All right, good afternoon. Hope everyone's doing well today. Let me pull up the homework because I know we got homework questions. All right. So week 10, we've pretty much made it through the course. We have one unit left, which we'll start today after finishing up some graph theory, and that last unit is grammars and languages, and it's one of the more fun topics in this course, I think. So let's see. Question in chat for directed graphs. How's the Euler theorem work? I'm not positive. For the homework question, I just wanted you to kind of look at it and try to find a path. But I think the theorem for a path is something like there has to be one vertex with out degree one more than in degree, and one vertex with out degree one less than in degree. And if you think about what a graph looks like, right, where there's vertices and directions, right, whatever this might look like. If you start at some point, every time that you leave, right, you're using up one of the out degrees. Every time you arrive, you're using up an in degree. If this is not where your path is going to end, anytime you enter, you also have to exit. And your goal is to go across all of the edges, which means for every line going into this point, if it's not your terminal point, for every edge going in, there has to be an edge going out, which means the degree in and the degree out are going to have to be the same. And there's going to be... Sorry? We can't see your screen. Oh, thank you. There we go. That's better. I can't move my... hold on. Alright, Zoom weirdness. Hold on. Gotta stop. Let's try that. Okay, that worked. All right. So picture a directed graph, right? And there's one vertex that you're going to begin at, and some vertex that you're going to finish at. Every other vertex in there, as you arrive, you're going to follow one of the edges that contributes to the in degree, and you're going to leave through an edge that contributes to the out degree, which means that the sum of all those in degrees must be the same as all the sum of the out degrees. Or the sum of the ingoing edges is the same as the sum of the outgoing. So your in degree and out degree have to be the same at every vertex, except for the vertex you begin at and the one you end at. The one you begin at will have, one greater out edge than in edge, and the one you finish at will have one greater in edge than out. So, so I think the criteria for a path is, at all but two vertices, the in degree and out degree match. At one of them, you have this relationship, and at the other, you have this relationship. And then for a cycle, I think all of them have to have the same in degree and out degree, because you have to terminate at the same place that you started. But for the homework question, right, rather than apply a theorem, I think you get more out of this by just playing around with this, trying to find a path, trying to find a circuit. And it's not that complex of a graph, so I think you can sort of just wiggle your way through and find out if there's a path, and if there is a path that starts and ends at the same point. Question 9, homework 4. That's pretty much how you went about it. Cool. Homework 9, question 4. How can D be connected to A if A is not connected to D? Question 9. Homework 9, question 4. Because it's a directed graph. So let's see what this graph looks like. So 1 1 1 0 0 0 1 0 1 0 1 0 1 1 1 0. And so we can think of this as from and to. And if you switch those, you just get a mirror image of the graph, which is fine. And where I put these on paper, it doesn't really matter. But this is saying, for example, there's a edge from A to A, and from A to B, and from A to C. For D, there's an edge going to every node, so there's one from D to D, D to B, D to C, D to A. And you do the same thing for B and C, figure out what those edges are, there's your graph. So everywhere that there's a 1 in this matrix, it means there's an edge from this vertex to whichever vertex the 1 is in. So A goes to A, B, and C. A does not go to D. But if we look at vertex D, D has an edge going to all of A, B, C, and D. So there's D connected to D, B, A, and C. And that's you know how you draw your directed graph. So an undirected graph, your matrix is going to be symmetric. If there's an edge from B to C, then there's going to be an edge from C to B. But in an undirected one, you don't need that symmetry, and in fact, you usually won't find that. All right, so other questions? Would there be an arrow from C to A? So the way I'm interpreting this, and like I say, there's some ambiguity, but I'm interpreting this as from here and to here. So would there be an arrow from C to A? Yep, there would be. And from C to C, and there would also be an arrow from B to C. But I didn't want to draw on all the arrows because then I've done your homework question for you. But that takes care of A and D. All right, good. Other questions? Okay, yeah, so I copied that wrong. That should be a 0. So there wouldn't be one from D to D. So good, I'm not doing your homework then. I did not finish drawing in this matrix. I'm not going to do the entire problem right here, right? Because you're not turning this in till Wednesday. So this is not the complete solution, etc. Right? This is showing some of the vertices to give you an idea how to draw the edges that correspond to, you know, the matrix. Plus that shouldn't be a 1 there, so it's just an example. But does that example make sense? Cool. All right, any other questions? right, so let's talk a little more about Dijkstra's algorithm. Hopefully people had some success with this, doing the homework. But let's go through and do a start to finish example where we record the path and where we do this in the way that you would do in order to show your work so that you could, hopefully get credit for this. So let's say our goal is to find a path from A to H. Find the shortest path from A to H using Dijkstra's algorithm. And this is our graph, okay? So the trick is, if I just keep, crossing out tentative distances and replacing them with relaxed distances and so on, when I'm done, if I don't have the right answer, right, there's nothing in here that sort of shows where I went wrong. So when you're doing this on homework, when you're doing this on the final exam, what you want to do is break your work up into different copies of your graph so that it's clear what you did in what order. Okay, so I just want to go through an example of that for future reference, right? So how to show work for how to show your work for credit on the homework and the final exam. So let's say we're going from A to H. Okay, so the first thing we're going to do, we're going to start off at the initial node. We're going to mark that with a distance of 0, and we're going to write in tentative distances for all of our other nodes. I don't know if I have enough copies of this or not, but we'll find out. Okay, and I'm going to label these graphs, This is my first graph, and I'll probably go across and down. Okay, so that's my initial setup. What I want to do now is remember the two-step algorithm, right? So visit closest node. And then relax adjacent nodes. All right, and when we visit, we basically circle the node, and then we know the shortest path and distance to that node. So we start off with just our source node visited with a distance of 0. Okay, so we want to visit the, we need to relax from that initial node first. So let's just put these in the other steps. So let's relax the distances from our initial node. Okay. And from A, I can get to this node with a distance of 1. So I'm going to cross out that infinity, and I'm going to say if I go through node A, I can get here in a distance of 1. And I can also get to this node C in a distance of 3. So instead of infinity, I can say if I go through node A, I'll get here in a distance of 3. And I can get to node B in a distance of 2. So I'll cross out my infinity and say if I go through node A, I get here in a distance of 2. All right, the next step is to visit the closest node that has not already been visited. Most of these are infinities. There's a 3, there's a 2, there's a 1. So I should circle this 1. Okay, if I circle the 1 on this graph, I don't know if I circled this first or I circled that first, right? My presentation of my work becomes ambiguous. So at this point, I'm going to go to a new copy of my graph, and I'm going to label these, accordingly. And this takes a bit of time. All right, I'm going to say, what's my closest node? Well, it looks like it's this one, which is vertex D, distance 1, so I'm going to visit that. And now I'm going to relax my nodes that are adjacent to vertex D. All right, so what's connected to this vertex that has not already been visited? I can go a distance of 4 to get down here. 1 plus 4 is 5. That's better than infinity. So this infinity gets replaced with, if I go through A and D I can get here in a distance of 5. Alright, this node over here, if I come through D for a distance of 1, and then I come another one over here, that's a total distance of 2. That's better than 3, so I'm going to relax that node, and I'm going to say I'm not going to do this with a distance 3 from A. I'm going to go through A and D for a distance of 2. And that's it for the nodes that are adjacent to this recently visited node. So I need to visit another node now. So again, I'm going to copy this information over. Alright, this has been visited. This is an A with a 2. This is an AD with a 2. This is an AD with a 5. And these are still infinities. Alright, so somebody tell me, what's my closest node that I have not visited yet? So F would be a distant, well, F is not directly connected though to nodes that I have visited. So B is a distance 2 from a node that I visited. So that looks like my closest node, right? Except for node C, which is only a distance 1 from a node I visited. So yeah, C is going to be my best choice. And if I had more than one node at a distance of 1, I could pick any one that I wanted. Okay, but C is a distance of 1. I'm going to go ahead and visit that, which means I'm going to circle it. Which means I know now that the best distance I can get from A to C is 2. I'm not going to find anything better. And a path for doing that is A followed by D. Alright, so now relax the nodes that are connected to C. And here's a node E. Well, 2 plus 2 is 4. That's better than 5. So we'll throw this away, and we'll say let's go A, D, C for a distance of 4. Here's another vertex that's a distance 8. So AD took us 2 plus another 8 will give us 10. That's better than infinity. So ADC gives us a distance of 10. If B was less than C, then we would have done B exactly. And if they were the same, we could have done either one, and the order wouldn't matter in the end. We would still get A shortest path, but it might not be unique. Alright, so I think that's it for relaxing nodes from C. So now we have to visit the closest node. And as people have already discovered, B looks like the closest node now. That's a distance of 2. This is also a distance of 2. So it doesn't matter if we do B or E next. Let's go ahead and do B. So that's 0, that's A, comma 1. This is AD, comma 2. This is ADC, comma 4. This is ADC, comma 10. This is infinity. And infinity. We forgot to relax a node somewhere. Oh, this is not circled. Okay. So A, comma 2, ADC, that's circled and visited. Alright, so we're going to visit the closest node, and we said we'll go ahead and do B. And now we relax nodes that are adjacent to B. Well, the only node that's adjacent to that is G. 2 plus 10 would be 12. That's not better than our current 10, so we're not going to change that distance. Alright, so this is getting really complex. And if I ask you to do this on the final, it's probably going to be a pretty simple graph. Or I might ask you to do a part of it. Alright, so this is where we are. So what's the closest vertex now? Yeah, so that's an E. That's this one right here, because that's a distance 2 from this. And so let's visit that. Alright, so we've locked in that distance. Let's relax vertices from there. So 4 plus 1 is 5. That's a good solution. So ADC plus E gets us here for a distance 5. And it looks like that's the only vertex that's connected that we haven't already visited. This is why computers are so nice, 'cause a computer will do this for you. You don't have to keep writing stuff and making multiple copies and all that sort of stuff. Alright, so someone... Okay, so what's our closest vertex now? This looks like a distance of 8. This looks like a distance of 1. So we're going to visit that. And at this point, I'm going to get sloppy. In the interest of time, I'm going to stop continually recopying all of this information that I've already got, because I've only got 2 vertices left. And I think we've got the idea of this. So I would relax the edges that are adjacent to F, right? So 5 plus 1 is 6. That's a better solution. So A, D, C, E, F gets us here in 6. And here we have a distance of 2 plus 5 is 7. That's better. So A, D, C, E, F gets us here in a distance of 7. And then we would visit this node, because that's a distance of 1. This is a distance of 2. So we mark this node as visited. We relax distances. 6 plus 2 will be 8. That's not better than 7. So we would not relax, and then we would visit our last node here. So this will actually end up being our final configuration. And so to go from A to H, which was where all of this started, right? We're told our shortest path is A, D, C, E, F. So A, D, C, E, F, and then H. And so 1, 2, 3, 4, 5, 6, 7. All right, that's Dijkstra's algorithm. It always works. It's very efficient. If you have n vertices, it basically takes you n iterations of a main loop. And in that loop, you simply need to know which vertex is closest to your visited vertices, so you can visit that node and then relax the edges, which is, you know, on the order of how many vertices that new vertex is connected to. So it's an efficient algorithm, and it's way more efficient than you know, just kind of exhaustively trying all possible paths. But it does not work with negative weights. If you have negative weights, then you have to go with more complex algorithms. Yeah, there's other ways we could structure this to record what happens at each step, and I may try to come up with something like that if I want to ask you a more aggressive Dijkstra's algorithm question on the exam. But I think I'll probably give you something with just a small number of nodes, just to illustrate. Yeah, A star is a good algorithm. A star is a variation on this, but I'm not terribly familiar with it. And this is a variation on something that that I called ants at a picnic, which was if you have, you know, a matrix and you have some connections present and some missing. And you want to get from, say, one point to another, right? So picture an anthill over here and a picnic basket over here, right? And your ants are perfectly uniform, they move at the same rate. And so at each vertex, you simply split up your ants into, you know, up to 4 subgroups to go out in all possible directions. And, you know, at first all the ants have to move here. And when they come down here, right, now they can split. So half the ants go this way, half of them go this way. And at this point, you know, these ants continue down here, half of these go down here, half of them come out here. By definition, the first ant to reach this destination has followed a shortest path, right? Because time is being mapped to path length. And so if you simply farm out in all directions, the first thing that gets you to your target is, by definition, following a shortest path. And that's a version of Dijkstra's algorithm where all of your weights are the same. Or maybe where you increase your speed based on the weight of an edge or something like that. So there's like physical analogies to this. This is also how you make like a paint fill program work on GIMP or software like that, where you do a paint bucket to fill. You just go out in all directions until you hit a border, and that's an efficient way to fill a space. Precedence graph. So I didn't mean for precedence graphs to be really wonky. Right, this is just an example of a graph of in this case relating instruction dependence. So let me make some instructions. A equals 5, B equals 10, C equals A plus 3, D equals B plus C, E equals B. Well, I guess I can just use these as is. So A equals 5 doesn't depend on anything. B equals 10 doesn't depend on anything. C equals A plus 3 requires that this instruction finishes first. So I'm going to draw an arrow from this instruction to that instruction, which means if this instruction is trying to figure out when it can run, it needs to look at this instruction and wait for indication that this has completed. As soon as this is completed, this instruction can execute. All right, D equals B plus C. Well, that needs to know the current value of B and C, so that instruction has to look for 2 dependencies to be satisfied. That's these 2. And then E requires B to be finished, so E equals B. That's dependent on this instruction. So that would be a precedence graph. But from analyzing this, we can tell indirectly, for example, this instruction also depends on the completion of this instruction, which might be useful information if something happened to change this instruction, right? We might need to know that we have to redo these instructions and so on. But for the graph theory aspect of this, it's just a way to show which instructions are reliant on other instructions. Yeah, I've written some old bucket fill programs that took 30 seconds or more to fill. Those are always fun. What would happen if one of the letters changed value again, say B equals 15, between steps 4 and 5? So if we put in b equals 15. So I would say b equals 15 cannot happen until step 4 finishes, because step 4 is using the previous value of b. So this would be dependent on that. And then this e equals b would be dependent on that. Does that make sense? This is one of these things that's usually not too bad for us to sort of sit down and just kind of work out a graph. But if you tried to write a program that could analyze this code and come up with a graph, that can be tricky, right? Especially things like this where you know, this doesn't depend on D, for example, but this b equals 15 can't be allowed to execute until statement 4 is finished, because if b gets changed to 15 first, D's not going to be using the proper value of b, which should be 10 at that point. So it's almost like a backwards dependency. So trying to do some automated analysis from this to get this graph can be tricky. But you know, stuff like that happens inside your compiler and or inside your execution unit of your CPU. And it's pretty cool that that all works. All right, other questions? How will we find the length of a path in number 6 on the homework? Can you tell I got some CPU lag? So suppose we wanted to find a path from A to C, right? The length would be 2. Well, no, the length would be 3. So from A to B, and from B to E, and from E to C, that would be a length of 3. So the length is just the number of edges in this case, because it's an unweighted graph. And so this is asking you if going from, you know, one vertex to the next represents a path. In other words, are the edges connected? And if so, what's its length? Well, its length is, you can pretty much get it from the number of vertices. So A, B, E, C, B goes from here to there, to there, to there, to there. So what's the length? 1, 2, 3, 4. And it's got 5 vertices. So the length is always going to be 1 less than the number of vertices in this case. Did we count the number of edges if it travels the same edge more than once? Yes. So think of this as, you know, walking through the woods, right? How far do you walk? And if you go from A to B and back to A and back to B, you've traveled a distance of 4, right? So you count 4 edges there. Even though the total distance you've moved may only be, you know, 1 or 0 if you come back to where you start. So yeah, count with multiplicity. All right, so let's see. Reminder, there's no class on Wednesday, so Wednesday is listed as a faculty work day. And then Thursday, Friday are holidays, so we don't meet again until a week from today. And I may post some homework for this last unit, or I may just skip it, because I'm not sure how much sense the homework's going to make, because I don't think we get a chance to talk about it until Wednesday, which means you could turn it in on Friday and I'd never get it back to you. So I don't know if we're going to do homework for this last section or not. We may skip it. But we will meet again a week from today, and that will be a short class because I've got to go to this faculty thing at 1. but I may post a video for you to watch for the last hour of that class. But let's get started today talking about this last unit, which is languages and grammars. And we'll skip over the tree stuff because we're going to talk about trees in CSE215. So we'll go on to this next unit, which is languages and grammars. And this is also a subject that you'll encounter elsewhere. So again, this is kind of a first pass if you haven't seen this stuff before. And what is language? You know, it's a way to communicate, to convey information. So as humans, you know, we have language that we use to share information and ideas. But there's also, you know, things like computer languages, which we use to share information and ideas with a computer. And computer languages have very rigid rules because computers aren't very good at language, right? So humans, you know, we can talk casually, we can repeat ourselves in the middle of a sentence, we can throw in things like the word for example, and still convey the meaning, okay? Computer language is very rigorous because we have, you know, computer programs that are interpreting them. So we want to think about languages and how we describe languages and so on, largely for the sake of, you know, dealing with computers, writing compilers that take something like a bunch of C code and interpret it as here's what I should write a program to do, and then create an assembly language program to do that, assemble that, link it, and so on. All right, so the first thing is there's a distinction between syntax and semantics. All right, we're only talking about syntax. We're not going to discuss semantics. And this is appropriate, right? So for example, I can write a C program which says, you know, integer main. If 1 equals 2, j equals 1 divided by 0, j equals 10, j equals 2, j equals 0, return. Syntactically, is that a valid C program? Absolutely. It says if 1 equals 2, set j equal to 1 divided by 0, and then set j equal to 10, 2, 0, and then return. Perfectly complete syntax, right? No problem with this. You run this through a C compiler, you won't even get a warning. I don't think. Maybe you'll get a warning on that. But semantically, as far as the meaning of this program, it's meaningless, right? This doesn't do anything except take some CPU time, load some values into memory that we never use. So semantically, this is kind of a mess, but syntactically, this is perfect. Okay, so we're only talking about syntax. We're talking about the structure of a sentence, for example, not the meaning of it. All right, and so we're interested in formal languages. And so let me give you an example of a really simplified version of English that counts as a formal language. So let's describe a sentence. And I'll say a sentence is a noun phrase followed by a verb phrase. So the dog barks. All right. Well, that's great, except we don't know what we mean by a noun phrase or a verb phrase, so we have to specify those. So a noun phrase could be described as an article followed by an adjective followed by a noun. Or it could simply be an article followed by a noun. Okay, what's an article? It's something like the or a. An adjective is something that embellishes a noun, and a noun is a thing. Right? So the hungry hippo would be an example of a noun phrase. The hippo would be another example of a noun phrase. A hippo would be another example of a noun phrase. All right. A verb phrase can be one of two things. It can be a verb followed by an adverb, or it could just be a plain old verb. So a verb is an action word. Runs, eats, jumps, laughs, cries. And an adverb embellishes that verb. Runs quickly, laughs slowly, cries happily. All right, well that's great, except, we have to know what these things are: article, adjective, noun, adverb. So we can say article equals the or a. And I'll start moving across so that I don't run out of paper. An adjective could be, large or happy. A noun could be a bunny or a laptop. A verb could be, eats or laughs. And an adverb could be loudly or quickly. So what I've got here is a formal description of what a sentence is. It's a noun phrase followed by a verb phrase. And we can do two things with this description. One, we can take something and say, is this a sentence? And we can see if it matches this template. So we can use this to do syntax analysis. So for example, the happy laptop eats quickly. And we can say, is that a sentence? And so when I was in grade school, they had stopped diagramming sentences. I think they started after I finished grade school. But there's this idea of diagramming sentences where we can say, this is a noun phrase, and this is a verb phrase, and this is an article, and this is an adjective, and this is a noun, and this is a verb, and this is an adverb, right? And you basically take this thing and try to put it into this template, right? So it's a little like 270 trying to reverse engineer binary code, right? And there's different ways we could do this. We could try to break it up like this and say maybe this is a noun phrase and this is a verb phrase. Well, the happy, if that's a noun phrase, this would have to be an article and a noun. Nope, that's not a noun, so that doesn't work. And the question of how to split this up to confirm that this is a sentence, right? That's a tricky process. It's one of these processes, though, that's really easy for a computer, and we can write a program that will do this really easily. But for us, looking at this and looking at this definition of a sentence, it may not be clear how to split this up to confirm that, yes, this is a sentence because it's a noun phrase followed by a verb phrase. That's a verb phrase because it is a verb which is eats, followed by an adverb, which is quickly, so it's a verb phrase because that can be a verb phrase. Yeah. Okay. So that's one thing we can do. We can analyze structure. The other thing we can do is we can construct sentences using this. Okay. We can simply take any noun phrase and verb phrase, put them side by side, and get a sentence. How do we manufacture a noun phrase? Well, we could either take an article and a noun, put them next to each other, or take an article, an adjective, and a noun and put them next to each other. Right? Which was what I did in my head when I wrote down this sentence. I just kind of like pulled out some of these pieces and put them together in this way so that the thing we end up with is a sentence. Right? So this is a Mad Lib, right? That's all that Mad Libs are. They're fill in the blank, and whatever you end up with will syntactically be correct, even if the semantics, the meaning, are silly, which is why Mad Libs are fun, right? Because you get something that's a perfectly valid sentence, but it means silly things. Or you can use them as fortune cookies, which is good. Decide what to do that day. All right, so that's an example of a formal language description. And so you can come up with large bunnies calculating pi and things like that. Just worried about the syntax. All right, so we're going to come up with some definitions. Pro tip, a semicolon can be easily described as something that replaces colon, quote, comma, for, comma, but, comma, and quote, and other conjunctions. Ah, yes, that's true. I get that. Cool. All right. So we're going to do some definitions here, and our goal is to come up with a different way to describe a language, right? Because this is a good way, and we'll see something called BNF later on, which we can use to describe a language in this style, and BNF is a really efficient way to describe something like C, right, or other computer languages. But we're going to look at a different approach to this, which is something called a phrase structure grammar. Okay, that's where we're heading. In fact, I'll tag that. All right, so we need some terminology here. So we'll start with a vocabulary. So vocabulary V is a finite, non-empty set of symbols. So we're going back to set theory. A word, which is also sometimes called a sentence. When we talk about a word or a sentence over vocabulary, so a sentence over V is just a string of symbols from V. So is a finite length string of elements of V. So vocabulary is just a set of symbols. A sentence over vocabulary is a finite length string of those symbols. Okay, so repetition is allowed. It's just a string of elements coming from that set. All right, so you can think of our vocabulary as being letters of the alphabet, and words being, you know, collections of those letters side by side. All right, we use the symbol lambda to represent an empty string. Okay, and this is not the same thing as an empty set. Okay, this is a string. It's a finite length collection of elements of V. That collection might contain 0 elements of V. That's valid, but that's called an empty string or a null string. Okay, slightly different from an empty set. All right, a V with an asterisk on top is a set. It's the set of all words over V. This is the asterisk we see in regular expressions, by the way. So if you've been playing along in 224, when you say like something asterisk, that's where that comes from. All right, so now we can describe what a language is. So a language over V is just a subset of V star. All right, so think about how this all goes together, right? We've got a collection of symbols, right? That's our vocabulary. A word over that vocabulary is just a string of symbols from that vocabulary. And V star is the collection of all words, all finite length strings made up of symbols from that vocabulary. And a language over V is just a subset of V star. So it's a particular collection of words where each word is a finite length string made up from symbols of the vocabulary. So if we try to do this in analogy to, you know, the English language, for example, we could think of the vocabulary as the letters A through Z. A word is a collection of letters, right? With the possibility that, you know, there's a 0 length word. But it's just a collection of letters, right? It could be any collection of letters. A, Q, Q, Z, right, would be a word. V star is the set of all words. That's an infinite set because there's no limit to how long these strings can be, even though each one is finite. So V star is basically the set containing all possible combinations of letters of any finite length. But then a language over V is some subset of this. This could be the words that we find in the dictionary, right? Which is just a particular set of strings of these symbols. And that's what we call the language. Or bracket AZ, AZ. Yeah, throw a star at the end and then you got V star. So 0 or more occurrences of the letters A through Z. All right. So this language, you know, would be, say, you know, English language or you know, language for some course or something like that. All right. So our question is, how do we specify a language? How do we describe what the valid words are in this language? And there's different ways we could do this. So think about C programming language, right? What is our vocabulary look like? Well, it's basically the ASCII character set, at least the printable characters. We don't usually write programs with Control-G in the middle of them. But, you know, letters, digits, punctuation, right? That's the vocabulary. A word is a finite length string of elements of that. Well, every program that we write, correct or incorrect, is a word, right? Or a sentence over that vocabulary. The language that we call C is a subset of all of those possible words. We could think of the language of C as the collection of all syntactically valid C programs, which is a little bit of a weird way to think of a language. All right, so how do we specify a language? There's one option, which is to simply list all the words that are valid over V. So we could specify the syntax of C by simply writing out every possible syntactically correct C program and say there's the specification of the C language. Would that be a reasonable thing to do? Right? You probably don't want to write a C compiler that way, by giving it a file containing every valid C program and then just matching to see if the person's program matches one of these. You can't do that, right? But we do this in another case, right? This is what we do in English. This is what a dictionary is. It's a list of all the valid words in the English language. And you're playing Scrabble, you want to know if this thing's a word. What do? You look it up in the dictionary and say, oh no, that's not a word, right? And that's really like, you know, the main way that we know if something is a word or not. So is abracadabra a word? Well, I mean, it's pronounceable, but, you know, is it actually a word? There's no rule we can use to answer that question. We have to kind of resort to this list. Right? So sometimes this is the way that you specify a language. Okay, a different approach is, you know, list rules for a word to belong to the language. I shouldn't have said in V star up here. I should have said in the language. Okay, we could list rules. Abracadabra B. Right? So what are some rules we have? Well, if you have the letter Q, it's got to be followed by a U, mostly. If you have a word, it's got to have at least one vowel in it, mostly. So we have some rules we can use to immediately say, you know, this is not a word. But those don't give us, you know, 100% information, which is why you can write a program to create things that sound like words, but actually aren't. So if you go into Tinkercad and you start a new design, it creates some pronounceable name for your project, which is usually a nonsense word. But it's pronounceable. It follows some of these rules we have for things to be words, but that's not enough to say that something's a word. But in C, we could do this, right? We can list specific rules for whether or not a program is syntactically correct. For example, you got to have a semicolon after almost every statement. You got to have a space between the word int and the name of a variable. Your variable can't begin with a digit, or a dollar sign, or a number sign. If you find 2 slashes, you can have anything after that to the end of the line. So we could, you know, make a set of rules for identifying C syntax. So there's different ways to do this. Okay? The approach we're going to take is describe a grammar. So what is a grammar? It's basically rules for producing words. And we're going to work with a particular type of grammar, which is a phrase structure grammar. So a phrase structure grammar G is a four-tuple. It's a collection of four things, which we call V, T, S, and P. Okay, V equals the vocabulary. T equals the set of terminal symbols. S is what we call the start symbol. And P is a set of production rules. So these four things will describe a grammar, a language for us. Okay, so V is the vocabulary. It's the symbols from which our words are constructed. T is a set of special symbols which we call terminal symbols. This is a subset of our vocabulary. S is a start symbol, which is contained in the vocabulary. And P is where all the magic happens. Alright, so we're just going to do a bunch of examples of this. And this is one of these things that watching somebody do it will generally make sense. Doing it yourself will feel very different. Kind of like physics. Kind of like programming. So we'll go through a bunch of examples and you'll have some problems to work on. Graded or ungraded, I don't know. But you'll have some homework problems to work on to get some practice with this. Alright, so let's do some examples. So we'll start with grammar. VTSP. I'll stop writing that pretty quickly. Our vocabulary consists of the following symbols: little a, little b, big B, and S. Would the semicolon be a terminal symbol? I've never written a phrase structure grammar for C. But yeah, all of the ASCII characters would actually be terminal symbols. And you'll see why in a second. So our terminal symbols, in this case, are going to be little a and little b. This means that our actual words in our language are going to be made up of just these symbols here. Okay, A, B, and S are sort of temporary symbols that we can use in interesting ways. But the things that we come up with in the end, the words, are going to be composed of just those terminal symbols. Alright, our start symbol is going to be S. That's usually not very interesting. And then we have a set of production rules. Okay, so our production rules are a set, and they have the following form. For example, S goes to A, B, A. Big A goes to uppercase B, uppercase B. Uppercase B goes to little a, little b. And uppercase A, uppercase B goes to B. Alright, those four things describe a language. Alright, so what language does this example describe? Here's how you interpret this. You have to start with the start symbol S. So I'm going to start with just an S. And I can use my production rules to change something into something else. For example, I can change S into an uppercase A, an uppercase B, and a lowercase a. Okay, this is not yet a word over my language because it's not made up of just terminal symbols. But for example, this AB can be changed into a B, which means from my start symbol I could go to uppercase A, uppercase B, lowercase a, which means I could go to just lower b, lower a. And that's a word over my language. On the other hand, I could have said, let me just do a separate picture over here. S goes to A, B, A. Well, A could have gone to two B's, so this could go to B, 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 A. And my uppercase B could go to a little a, B. So this could go to A, B, A, B, A, B, A. So that's another word over my language. And it turns out those are the only two options I have. Now I could have also said, you know, S can go to A, B, A. And I know a B can go to a little a, B, so this could go to A, and my B goes to a little a, B, and my A goes to an A. And then my A can go to two B's. And each of those B's can go to an A, B. And so I end up with the same A, B, A, B, A, B, A. So there's really only two words in this language, BA and Abba, Abba, without the final. Actually, Abba, Abba, Abba. All right, so why do we want to do this? What does this have to do with languages, right? This is arguably a way to start from a start symbol and go through and, you know, derive different words. So it's kind of like a Mad Lib, right? Okay, let me give you a few more definitions and some formalism, and we'll see why this works to help us describe languages. So suppose we have some symbol W0, which is some, you know, left piece followed by some middle piece followed by some right piece. And suppose we have some other symbol W1, which is the same left piece followed by a different middle piece followed by the same right piece. And suppose that there is a rule which says Z0 can be replaced with Z1. Suppose that's in our set of production rules. Okay, if these things are true, then we have the following terminology. We say W1 is directly derivable from W0. Okay, if W0 is a bunch of stuff with a Z0 in the middle, W1's the same stuff with a Z1, and we have a production rule to change 0 to Z1, then this string is directly derivable from that string. Right? And that's all we were doing in here when we would say, you know, ABA would be replaced with BBBA, right? This was the right part, was the BA. The left part here happened to be the empty string, and the middle part, A, could be changed into BB because we had a production rule, A goes to BB. So saying something is directly derivable from something else means if we were drawing those out, we could just replace that first thing with the second thing. Okay, and when we say W1 is directly derivable from W0, we write that as W0 double arrow W1. This has nothing to do with propositional logic. Okay, this is a totally different subject, but we're reusing the symbol of this double implication. This means directly derivable from. All right, if it turns out that W1 is directly derivable from W0, and W2 is directly derivable from W1, and so on, up to and including, you know, some Wn. So each of these is directly derivable from the one before it. then we can say Wn is derivable from W0. It's also derivable from W1, W2, and so on. And it's directly derivable from Wn minus 1. But it's derivable, right? There's a chain rule here. Because, you know, if you apply this idea, we could take W0 and change it into W1 with some production rule, change that into W2, and so on. And so here we write W0, arrow, Wn. We put an asterisk on top. That means derivable, but not necessarily directly derivable. And this stuff up here, that's called a derivation. That's the way that we get Wn from W0, or a way. All right, so derivable, we can use one production rule, followed by another, followed by another. Directly derivable, one production rule. All right, so now we're ready for the super duper definition, and we'll end our class after this. So definition, the language generated by G or sometimes we just call that the language of G. And that's L of G equals the set of all strings of terminal symbols derivable from S. Alright, so starting with whatever the start symbol is S, any string that we can derive from that, that's part of the language. So the language is the collection of all strings composed only of terminal symbols that can be derived from S. Meaning there's a linkage of direct derivations, right, from here to here to here to here to here, ending with a string of terminals. That makes this part of the language. And we can write that succinctly. It's a set of words It's a set of words contained in the collection of all finite length strings of terminal symbols such that there is a derivation from S to W. So all of that lecture boils down to this, right? That's the very succinct notation. So the language of G is the set of all strings comprised of terminal symbols such that that string is derivable from the start symbol. So back on our first example, right, the language is, the set containing these two strings. Those are both members of T star, and they were each derivable from S. And here's a derivation showing how we can get to those. Here's a second derivation for getting to this word, right? All right, so So I won't see you for a week. I'll see you briefly on Monday, and we will go through some examples of languages and just play around with this and see what kinds of words we can get out of these languages, based on the production rules in particular. And it's mainly the production rules that capture the essence of the language itself. So we'll play around with that on Monday. I will post some homework questions. Like I said, I don't know if I'm going to collect them or not. I'll make a decision and I'll let you know in the posting, but I'll get that up later today or tomorrow. And I will probably have a video for you next Monday to watch after I disappear at 1. So we'll play with specific languages at that point. And then I want to talk a little bit more about parsing Bacchus-Naur form BNF, tie this into state machines, finite state machines from Engineering 250. And then I want to wrap up by talking about Turing machines, which are a particular type of finite state machine, and they're basically the origin of all of our computers that we use today, artificial computers. Those are all Turing machines. So we'll play with Turing machines hopefully on Wednesday, and talk about a few consequences of that, including the halting problem, and questions of P versus NP, traveling salesperson problem, and so on. So we're in the end game for sure. Have a fantastic break. Let me know if you have questions. I will post some homework to work on. And I will see you, if I don't see you in 224, I will see you next Monday. All right, thank you. Have a good one.